Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in. Let's go through all the probability you need to know for Wednesday's task. So I've divided the video up into these 4 sections, but before we get into those, I will go through what probability actually is. So probability is the assigning to random events a number to indicate how likely it is to occur. So note we're only focused on random events, not events that are controlled by someone or something. So what is the number that we give it? So remember we have our number line and the probability of an event needs to be between 0 and 1. Of course, the closer the probability is to 1, the more likely it is to occur. So events with probability close to 0 are unlikely to occur. Of course, if an event has probability 0, it's impossible. Probability 1, it is certain. So if you are asked, what is the probability that blah, 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 you must give a number, and that number has to be between 0 and 1. Whether you give it as a fraction, decimal, or percentage, it doesn't really matter. So what is the way that we calculate the probability of an event? So sort of the central dogma behind probability, the probability of an event is the number of ways it can occur over the total number of outcomes. So the total number of outcomes is NS for number in the sample space. So all of what we do in probability is basically to figure out this ratio here. What is the proportion of the number of ways an event can occur to the total number of outcomes? So let's get into unions, intersections, and Venn diagrams. Let's look at the information we have here. A class of 30, 16 people play soccer, 12 cricket, and 7 neither. So Venn diagrams and two-way tables are very useful in situations like these, where we have information about sets. So here we have 2 sets, set of students who play soccer, set of students who play cricket. So Venn diagrams and two-way tables give us a convenient way to display how many are in each set or both sets or neither. So we're going to draw up a Venn diagram and two-way table now to display this information, but I want you to know that Venn diagrams and two-way tables do exactly the same thing. So you don't really need to draw both. I'm just going to show you how to draw both. So Venn diagrams always look like this. So you have a rectangle and then 2 circles in the middle of the rectangle. So each of those circles represents a set. So I'm just going to call my sets A and B. Of course, the sets I'm interested in are people who play soccer and people who play cricket. So in the Venn diagram, we need to populate it with 4 numbers. So the number that goes there is A but not B. So these are the people who play soccer but not cricket. Then, of course, the other possibilities, you can play both. You can play cricket only, but not soccer, or you can play neither. So you might be thinking I've gone crazy because 16 plus 12 plus 7 doesn't equal 30. It's more than 30. It's 35. But that is possible if I've double counted some people. So however many you have over counted is how many are in both. So 16 plus 12 plus 7 is 35. That means I've counted 5 people twice. That means there are 5 people who play both. So what number do I put here in this box? Well, I know that 16 play soccer. So I want 11 in this circle here, the soccer circle. But I've already got 5 in that circle. So I need 11 more. So now there are 16 in the soccer circle. So similarly, I want 12 in the cricket circle. I've already got 5, so I need another 7. And then 7 play neither. That's how many go outside the Venn diagram. So let's now put this in a two-way table. So I've drawn up the two-way table here. It shows you how many are in each set or not in the set. So note, A dash means not A. The dash means not. So this is what the two-way tables always look like. Now the 4 numbers that go in these 4 cells here are the same 4 numbers in the Venn diagram. So this first cell we have here is the number in A and B, so soccer and cricket, and that is 5. So our next cell along here not A because it's in this column, and it's B because it's in this row. So not cricket and soccer. They play cricket only. So that's these 7 people here. Similarly, this cell here plays soccer but not cricket, and the other cell plays neither. So the 4 numbers in the Venn diagram are the 4 middle cells of the two-way table. So a difference between the Venn diagram and two-way table is that we have a row for totals in the two-way table. So this number and this number should add to 30, as should this number and this number, because there were 30 people in total. So this just allows us to display how many are in each set, neither, or both. Now, that will make probability calculations much easier. So just before we go to some probability questions, you need to know these symbols. This symbol here, the N, means intersection or and. And this one here means union or. So the N means and, the U means or. Let's now do some probability questions. So if I said the probability of A and B, that's what this says here. That's really simple now that I've got the Venn diagram and two-way table. It's just the number who plays soccer and cricket. This number, 5 out of 30. Okay, and I should simplify the fraction to 1 over 6. So what about if I wanted to figure out the probability of A or B? So this is saying what's the probability that a student selected at random plays soccer or cricket? It really means what's the probability they play soccer, play cricket, or both. So there is a formula for or. It's called the addition rule, because to find the probability something is A or B, you add the two probabilities together and you subtract the probability that both happen. So that here is the addition rule. So what's the intuition behind it? Well, the people who play soccer or cricket are these people plus these people, but hang on a minute, I double counted the middle. I counted it in soccer and cricket, so that's why I need to subtract it. So here, the probability of A or B is the probability of A. So there are 16 people who play soccer, out of 30. Then there are, it says 12 people who play cricket out of 30, but we have to subtract the probability that somebody plays both because we've counted those people in soccer and cricket. So if you just put that on your calculator, you get 23 out of 30. So again, note, when I was asked probability questions, my answer is a fraction. It is a number between 0 and 1. So make sure you know the symbols and the addition rule and how to construct Venn diagrams and two-way tables. So what I'm going to do now is I'm going to rub out the two-way table and quickly go through conditional probability. So please pause and copy this down if you need. So let's now turn our attention to conditional probability. So a condition is like a caveat, something that needs to happen. So for example, your parents might say they will buy you a car if you get an A in maths. So getting an A in maths is a condition for you to get a car. So what are we talking about in probability? So we might want to know, say, the probability that A happens given that another event B has happened, because sometimes the event B happening affects the probability of A. So we write it like this: probability of A given B. So that line there means given. It is saying what is the probability that event A happens if I already know that B has happened. So there is an intuitive formula there. So I'm saying that what's the probability A and B have happened if I know that probability of B has happened? It's basically saying what is the proportion of times when event B happens that event A will also happen. So you just use this formula here. So this hopefully will make more sense when we try an example. So let's go back to my class of 30 where 16 play soccer, 12 play cricket, and 7 play neither. So I know that the probability of A, for example, because I shouldn't have rubbed it out, A was soccer and B was cricket. So I know the probability that if I pick a student at random, they play soccer, I know that that's just 16 over 30, okay? That's really simple, probability that someone plays soccer. But what would be the probability a student plays soccer if I know that that student plays cricket? So I'm picking a student at random who I know plays cricket, and I want to find the probability that they also play soccer. That changes things, because suddenly I'm not looking at all 30 of these people here. If I know that they play cricket, I'm just looking at the students inside this circle. So inside this circle, I'm saying, what is the probability if I pick one of those that they play soccer? So you can see clearly there are 12 inside this circle, and 5 of them play soccer. I am saying, if I know I'm in the B circle, what is the probability I'm also in the A circle? And that, of course, means I have to be in the middle there. So the probability of A given B is 5 over 12, intuitively. But let me show you how I would use the formula to come up with this. Well, the probability of A and B I figured out was 1 over 6, or 5 over 30. So the probability of A and B over probability of B, which was 12 over 30. And if you put that on your calculator, you do get 5 over 12. So make sure you know how to do conditional probability questions, both from a Venn diagram like I did here, and also using the formula. Okay, so again, conditional probability is saying an event has happened. What's the probability that another event also happens? Because sometimes knowing that an event has happened changes the probability that something else will happen. So just to give you a little more context behind that, let's say, I don't know, the weather that I'm looking at. So the probability that it rains tomorrow is going to be different depending on whether it rained today. So if it rains today, it's probably more likely to rain tomorrow than if it didn't rain today. All right, we're going to move on to our next topic, which is multiple events. So when I'm talking about multiple events, I'm talking about events that happen in stages. So you might toss a coin twice, or you might roll a die twice, you might roll one die, toss one coin. All of those are events that happen in stages. You do one thing, and there are some outcomes. Then you do another thing, and there are some outcomes. So there were 2 ways we looked at listing the outcomes of multiple events. We looked at tree diagrams and tables. So this is different from Venn diagrams and two-way tables. Venn diagrams and two-way tables were how we display information about how many were in each set. So here, with tables and tree diagrams, we're looking at ways to list all the possible outcomes of events that occur in stages. So let's look at some examples. So let's look at this question here. I picked 2 cards at random from a normal deck, one after the other with replacement. What is the probability that I pick 2 different suits? So this is not an easy question to do. But again, we have some tools to help us. The table and the tree diagram will both be used to list all the possible outcomes that will help us answer this probability question. So let's first look at the table. So we're picking 2 cards one after the other. That's why this is a multi-stage event, because I pick one card, so that's one event with outcomes, and then I pick another card, another event with outcomes. So the 4 possibilities for suits are hearts, diamonds, spades, and clubs. So I can get them first go. I can also get them second go. So what I want to do is list all of the possible outcomes. So I rule up my table, and I'm just going to list all of these one after the other. So hopefully you can see there should be 16 possible outcomes. So if I get a heart first go and heart the second go, my possibility here is heart, heart. And then I can have diamonds, hearts, and so on. You just fill out this table. So when I filled out the table, I have all of the outcomes. But note one thing, when you're using a table, all of the outcomes have to be equally likely. So they are, because when I pick a card, hearts, diamonds, spades, and clubs are all equally likely to come up. Because it's with replacement, that means I pick the card and I put it back. On my second go, hearts, diamonds, spades, and clubs will be with replacement. So let's see what it would look like when I draw a tree diagram. So what I do is I set up my tree diagram like this. So each column is like a new event, a new outcome. So for the first one, for the first pick of the card, I can get hearts, diamonds, spades, or clubs. So for each of those, I can get the same next time around. So from hearts, I can get hearts, diamonds, spades, or clubs. And the same here, if I get diamonds, I get hearts, diamonds, spades, or clubs, and so on. So when I've done that, I just list all the outcomes and follow the branches. So I've got hearts, then diamonds, hearts, then spades, and so on. Now, in this particular tree diagram, I'm not putting probabilities on branches. Why? Because all outcomes are equally likely. So hopefully you can see that I have the exact same, in fact, list of outcomes from both the table and the tree diagram. Really didn't matter in this case which one I used. Now, because all of these are equally likely, the probability of it getting any one of them is 1 out of 16, because there are 16 in total. So if I pick 2 cards at random from a normal deck, one after the other with replacement, what is the probability I get 2 different suits? So all I have to do is go and count the ones that have 2 different suits. So this one, this one, this one. In fact, it's all of them except the 4 ones on the diagonal. All of these ones I'm circling have 2 different suits. And it's the same from the tree diagram. It's all of these ones that I'm labeling with the dash. They all have 2 different suits. So either way you do it, the probability is 12 of those out of 16, which is 3/4, okay? So again, you can only use tables when all the outcomes are equally likely. But you can use tree diagrams even if the outcomes are not. So I'm going to show you an example of tree diagrams where outcomes are not equally likely, and we're also going to go through the difference between with and without replacement. Let's look at this question here. Bag contains 4 red and 3 blue beads, and I'm going to pick 3 of them, one after the other at random with replacement, and I'm going to calculate the probability that I pick at least 2 red beads. Now straight away, I hope you're thinking tree diagram, because this is a multi-stage event. It occurs in stages. I pick a bead, then I pick another one, then I pick another one. So let's look at the tree diagram. We're going to set it up similarly to how we set up the one on the previous slide. So we have 3 stages, so we have a different column for each stage. First pick, second pick, and third pick. So just as we did last time, I'm going to have a list for all my outcomes, but this time I need to have a list for probabilities, because I'm going to need to do some work to calculate the probabilities. Because this one's a little harder, because not all outcomes will be equally likely. So what are my possibilities? So each time I can get either red or blue. So that part isn't different than what we were just doing. So there should be 8 outcomes in total, because each stage there's 2 outcomes. 2 times 2 times 2 is 8. But what makes this more challenging is, as I said, each of these 8 outcomes won't have probability 1/8. They will have a different probability. So we go through and list the outcomes, as I'm sure you know how to do. What we're going to need to do that's different this time is put on branches the probability of that event occurring, because blue and red will not have the same probability of occurring at each stage. So I'm going to start with a branch here. So first go, there were 4 red and 3 blue beads. So my probability of picking red is 4/7, and of blue is 3/7. Now this is with replacement. That means if I took out a bead, I then put it back, and I can have the same number of red and blue beads as I did at the start. So all the reds are going to be 4/7 probability, and all the blues are going to be 3/7. So now that I've put all the probabilities on the branches, how do I calculate the probability of each of these outcomes? Well, what I do is I multiply probabilities along the branches. So the probability of red is this times this times this. So it'll be 4/7 times 4/7 times 4/7, which is 64/343. The probability of the next outcome, red, blue. So I follow the branches. It'd be 4/7 times 4/7 times 3/7. So this one does not have the same probability of occurring. This will be 48/343. And I go through and I do the same for the other 6 outcomes. I multiply the probabilities on the respective branches. So you might notice a pattern. If there are 3 reds, the probability is 64/343. Anytime there are 2 reds, the probability is 48/343. 2 blues, probability 36/343. And then the probability of 3 blues is 27/343. Now, all of these probabilities here should add to 1. Probabilities add to 1 in exactly the same way that percentages add to 100. So fortunately, that is the case here. You can double check if you like, so I know I've done something right. So what is the probability that I pick at least 2 red beads? So I go through and figure out which are those that satisfy at least 2 red beads. Well, this one here is at least 2 red beads, so is this, because at least 2 does include 2 red beads. 2 is at least 2. This one here and this one here. So it could be any of those 4 outcomes. So what I'm saying is, what's the probability I get this or this or this or this? So all 4 of those are mutually exclusive. You can't get this one and this one. They're all mutually exclusive. So what I need to do is add up their probabilities. So the probability that I get at least 2 red will be this one plus this one plus this one plus this one, because this is the OR rule. You add the probabilities. But they are mutually exclusive, so I can just add all the probabilities. So it'll be 64/343, so that's the probability of 3 reds. And then there are 3 lots of getting 2 reds. And that just gives me 208/343, which is a bit more than a half. So that's how we deal with tree diagrams when the outcomes at each stage are not equally likely. So what I'm going to do now is the same question, but I'm going to change it to without replacement. I've now changed the question. It's exactly the same question, except it's now without replacement. So you might be thinking, oh my God, do I have to listen to him go through this whole thing again? Well, no, you don't. Because without replacement, only a small part of this changed. The tree diagram is going to be very similar. The only thing that will change is the probabilities after the first go. So I'm going to rub them out now. Okay, so on the first go, because there's still 4 red and 3 blue beads, the probability of getting red on the first go is 4/7 and blue is 3/7. But if I get a red on the first go and I don't replace it, so I take it out, don't replace it, there are 3 reds left out of 6 in total. There's 3 blue left out of 6 in total. If I get a blue on the first go, and I take that out and don't replace it, there will be 4 reds left out of 6, and 2 blues left out of 6. So, how do I do the third? Well, I do it in a very similar way. So if I got a red the first go, then a red the second go, so there are 3 reds out of 6 left. If I take one away, it's going to be 2 left out of 5, and there'll be 3 blues left out of 5. If I get a red, then a blue, I've taken 1 red away, 1 blue away. So there will be 3 red and 2 blue left. So 3 out of 5 will be red, 2 out of 5 will be blue. Okay, and so on. So if I got a blue, then a red, I've taken away 1 red and 1 blue from what was there originally. There'll be 3 red left out of 5 and 2 blue out of 5. If I get a blue and then a blue, there'll still be 4 red left out of 5 and 1 blue left out of 5. Okay, so I did go through that quickly, but please come and let me know if you don't understand it. So the only thing that has changed when I changed the question from with replacement to without replacement are the probabilities on the branches after the first go. So the way we figure out the probabilities overall is still the same way. We multiply them. But this time, the probability of red, red, red isn't 4 out of 7 times 4 out of 7 times 4 out of 7. It will be 4 out of 7 times 3 out of 6 times 2 out of 5. And that reduces to 4 out of 35. So I do the same for the next ones. The probability of red, red, blue is 4 over 7 times 3 over 6, but this time it's 3 over 5. Sorry, that should be. Okay, so that's the only difference. The probability I get red, red, blue, I just put that on my calculator and get 6 out of 35. So I'm going to go and do the same for the other 6. I'm going to calculate their probabilities by just multiplying the probabilities on the respective branches. So I've gone and done that now. Again, all the probabilities here should add to 1, and they do, so I know I've done something right. So this has changed the probabilities. It's basically made it less likely that you'll get all 3 red or all 3 blue. The probabilities have slightly changed. So what's the probability I pick at least 2 red beads? Well, I'm still talking about the same outcomes, this one, this one, this one, and this one. And as I did before, I add them together. So this will be 4 out of 35, probability of 3 red beads, and there's 3 ways that I can get exactly 2 red beads. Okay, and that will just give me 22 out of 35. So the probability has slightly gone up, only slightly. It was 208 out of 343 last time, which is about 0.61. Now it's 22 out of 35, which is about 0.62. So it's only changed the probability I pick at least 2 red beads slightly, and that's because it was pretty much the same tree diagram, just with slightly different numbers. So that's how you do a tree diagram for without replacement. All right, there's one more thing we need to go through, and that is independent events. What does it mean if 2 events are independent? Well, informally, it means that the outcome of the first event doesn't affect the outcome of the second event. So there are heaps of examples of this. So let's say, for example, I toss 2 coins. Getting a heads on the first coin and getting a heads on the second coin are independent. It doesn't matter what happens the first time you toss a coin, the probability of getting a heads the second time is unchanged. It will always be a half. Tossing a coin and rolling a die, they are independent events. It doesn't matter what happens when you toss the coin, that doesn't affect the chances that you'll say get a 6 when you roll the die. It doesn't affect the probability of that at all. So what are some example of events that are not independent? Well, studying for your maths test, that event, and doing well on your maths test, they are not independent because studying for your maths test increases the chances that you'll do well in the maths test. Studying doesn't necessarily mean you'll do well in the test, but it just increases your chances. So those are events that are not independent. So aside from knowing what independence means informally, we need to know the formal mathematical definition. So formally, 2 events A and B are said to be independent if the probability of A given B is equal to the probability of A, or the probability that the two events both happen is just the product of their respective probabilities. So the first one is very intuitive. If the probability of A given B is the probability of A, it's saying that the probability of A doesn't change by knowing that B has happened. B has not affected the probability that A will happen. So note that these two statements here, these two formula are equivalent. If one is true, the other will be true. If one is false, the other will be false. So let's look at an example where I'm putting this into practice. So let's look at this example. I play a card game in which I win if I draw either an ace or a heart. So I'm just drawing one card from the deck. I win if it's an ace or a heart, otherwise I lose. And I want to know if me winning and the card drawn is red are independent events. So what I'm going to do is I'm going to check if this here, this formula holds. So let A be the event that I win, and B, the event that the card I pick is red. So I now have to calculate the probability of A, the probability of A given B, and see if they are equal. So let's look at first the probability of A, the probability I win. So if I draw a card from a normal deck, what's the probability it's an ace or a heart? So for this, I'm going to use the addition rule. So the probability that I get either an ace or heart, remember the rule is I add the two probabilities together. So I find the probability of ace plus the probability of heart, but I need to minus the probability that it's both an ace and a heart. So the probability that the card is an ace is 1 over 13. The probability it's a heart is 1 over 4 because there are 4 suits, one of which is hearts. And the probability it's an ace and a heart, so the only card in the deck that is an ace and a heart is the ace of hearts. And the probability of picking that is 1 over 52. So if you put this on your calculator, you should get 4 out of 13 as a simplified fraction. So that's the probability of A. So what is the probability of A given B? Well, we went through this formula before. It is the probability of A and B over the probability of B. So probability of A and B, what's the probability I win and the card is red? So what is the probability that I pick a heart or a red ace? So how many ways can I win with a red card? Well, there are 13 hearts in the deck, but I could also get an ace of diamonds. So there are 14 ways in total that I can win. So my chance of winning and getting a red card is 14 over 52. The probability of B, the probability the card is red is a half. So it's 14 over 52 divided by a half, which is 7 over 13, if you put that on your calculator. So the probability that I win is 4 over 13. The probability I win if I know the card I drew is red is 7 over 13. These are not equal. Probability of A does not equal the probability of A given B, and so we conclude that they are not independent. And that makes sense, because the card being red increases my chances of winning. I'm more likely to win with a red card than a black card. So the card being red and me winning are not independent. So the last thing I'm going to do is just show you how independent events make calculations quite a bit easier. So the second definition I had on the previous slide can be really useful in calculating the probability of multiple events. So the game I was talking about was I pick a card from a deck and I win if it's either an ace or a heart. So if I play that game 3 times and each time I shuffle the deck afterward, what is the probability I win 3 times in a row? Well, I figured out on the previous slide the probability that I win was 4 over 13. So what's the probability I win 3 times in a row? So I'm saying what's the probability I win and then win and win again? So because each time I play is independent of the previous time because I shuffle the deck, because winning the first go doesn't affect whether I'll win the second time I play the game, I can just multiply the probabilities. The probability I win the first go is 4 over 13. The probability I win the second go is 4 over 13. The probability I win the third go is 4 over 13. Now, because each of these are independent, I can just multiply the probabilities together. And I get something like 64 over 2,197. So if events are independent, the probability they both happen, or the probability they all happen, is just the probabilities multiplied together. Let's look at this example here. I toss a coin and roll a die. What's the probability I get heads and a number greater than 4? So if I toss a coin, the probability I get heads is half. If I roll a die, the probability I get a number greater than 4, so 4 is not greater than 4, it would be 2 over 6 or 1 over 3. So these two events are independent. The outcome of the coin does not at all affect the outcome of the die. So the probability they both happen, that I get heads and a number greater than 4, I just times the probabilities together and get 1 over 6. How easy is that? So independent events there save me some time. I didn't need to draw up a tree diagram or a table to list all the possible outcomes. I could just use the rule for independence. Okay, sorry for the long video. So I wish you best of luck in the test. Of course, it's more a project than a test. So make sure you know how to apply these concepts to things like probability games, just like I did in the revision sheets that are on the portal. So I strongly recommend that you look at those revision sheets and ask me any questions. Otherwise, this has been the luckiest maths teacher in the world. Have a great day.